For this problem, we need to find the Fourier series coefficients of this triangle wave. It's modeled by this equation, a sub n is equal to 1 over t times the integral over 1 period of x of t times e to the negative j 2 pi nt over big T, all with respect to time, where big T is the period of this periodic signal. In other words, when the signal repeats itself, we see at t equals 0, it has a value of 0 and then a positive slope. This next occurs at t equals 4, so the period is going to be 4 seconds. Next, we need to pick a region that we're going to integrate over. We can pick any 4-second region, so for example, from t equals 0 to t equals 4. However, this would give us 3 separate regions we have to integrate over. One where the slope is positive, this next region where the slope is negative, and the third region where the slope is positive again. Instead of this, we can pick the region from t equals 1 to t equals 5, which will just give us one negative slope region and one positive slope region. So we'll only have to integrate over 2 different regions. To find the x of t equation that we're going to use in these 2 regions, I'm going to draw this separately. It has a maximum value of positive 1 and a minimum value of negative 1. And at t equals 1, it begins sloping downwards to its minimum value at t equals 3. And then it slopes back upwards to its maximum value at t equals 5. So the slope of this negative portion is negative 2 over 2, or negative 1. And the slope of the positive portion is 2 over 2, which is 1. I'll write out the equation for the negative slope region. X of t will be, it'll have a vertical shift of positive 1, so it'll be 1. And since it has a negative slope of negative 1, we'll have minus, then t, and there's a right shift 1, so it'll be t minus 1. So x of t will be 1 minus t plus 1, or 2 minus t. And this is on the region from 1 second to 3 seconds. For this positive slope portion, it has a vertical shift, negative 1, and a right shift 3. So x of t is going to be negative 1 plus t minus 3, which is t minus 4, on the region from 3 seconds to 5 seconds. So now that we have our 2 x of t equations, we can set up the integral. A sub n will be 1/4 times the integral from 1 to 3 of x of t, which is 2 minus t, times e to the negative j 2 pi nt over 4. And the second integral from 3 to 5 will be the next x of t equation, which is t minus 4 times e to the negative j 2 pi nt over 4. I'm going to do a substitution here. I'm going to let a be negative j times 2 pi n over 4, which simplifies to negative j times pi n over 2, just so I don't have to keep writing this whole e expression each time. So this first integral will be 2 minus t times e to the at, which is 2e to the at minus te to the at. This first part can be evaluated directly. It's going to be 2 over a, e to the at. This next part we can use integration by parts. U will be t, du will be dt, dv will be e to the at, v will be 1 over a, e to the at, and it's u times v minus the integral of v to u. So it'll be t to the at over a minus the integral of 1 over a, e to the at. So it'll be 2 over a, e to the at, minus te to the at over a, plus e to the at over a squared, all bounded from 1 to 3. I'll plug in these bounds. We'll have 2e to the 3a over a minus 3e to the 3a over a plus e to the 3a over a squared minus 2e to the a over a minus e to the a over a plus e to the a over a squared. Some of these terms will combine. We have this 2e to the 3a over a, and this negative 3e to the 3a over a. That'll just become negative e to the 3a over a. And I'll bring this term down. Next, we have these two terms which combine, and we'll have minus e to the a over a. And lastly, I'll bring that term down, plus e to the a over a squared. That's it for the first region, between 1 and 3 seconds. For the second region, it's te to the at minus 4e to the at from 3 to 5 seconds. We already did the iteration by parts for that first part, which we found it was te to the at over a minus e to the at over a squared. And for this next part, we can evaluate directly. It'll be minus 4e to the at over a. All that will be bounded between 3 and 5 seconds. I can plug in those bounds. It'll be 5e to the 5a over a minus e to the 5a over a squared minus 4e to the 5a over a minus 3e to the 3a over a minus e to the 3a over a squared minus 4e to the 3a over a. Again, some of these terms will combine. We have this 5e to the 5a over a and this negative 4e to the 5a over a. That'll become e to the 5a over a. I'll bring this term down. We'll have minus e to the 5a over a squared. And then over here, we have a 3e to the 3a over a and a negative 4e to the 3a over a. That would become negative e to the 3a over a. But we have this negative sign, so it becomes positive e to the 3a over a. And lastly, I'll bring this term down here. We'll have plus e to the 3a over a squared. That's it for the second integral. I'll copy these values down here onto one line. So it's plus e to the 5a over a minus e to the 5a over a squared plus e to the 3a over a plus e to the 3a over a squared. And all that had the 1/4 in front. Now some of these terms will also combine. We have this negative e to the 3a over a and this positive e to the 3a over a. Those will cancel. We have this e to the 3a over a squared and this other e to the 3a over a squared. That'll become 2e to the 3a over a squared. None of the other terms can be combined, so I'll just write them down here. We'll have this negative e to the a over a, then e to the a over a squared, plus e to the 5a over a, and minus e to the 5a over a squared. Since we have some common denominators with these a squared and a, I'm just going to write them together. We have 2e to the 3a and e to the a and negative e to the 5a all over a squared. And we have a plus e to the 5a minus e to the a over a. And all that has the 1/4 out in front. So this is our a sub n equation. There's one final thing we need to do, and that's to find the zeroth harmonic, also called the DC component. Its equation is this. It's 1 over t times the integral over 1 period of x to t dt. And again, we'll use the same two integrals we had before. It'll be 1/4 times the integral from 1 to 3 of 2 minus t. And the second integral was from 3 to 5 of t minus 4. For this first integral, the integral of 2 will be 2t. The integral of negative t will be negative t squared over 2. That will be bounded between 1 and 3. For this next one, the integral of t will be t squared over 2. And the integral of negative 4 will be minus 4t, bounded from 3 to 5. I'll plug in these bounds. 2 times 3 will be 6. 3 squared is 9. It'll be 9/2. Then it'll be minus, I'll plug in the 1, 2 times 1 will be 2. It'll be minus 1 squared will be 1 divided by 2. Then for this next one, we'll have 5 squared, which will be 25 divided by 2. Then 4 times 5, which is 20. Then I'll plug in the 3. We'll have 3 squared, which is 9. Then divide by 2. And then 4 times 3, which will be 12. Over here we have 6 minus 9/2, and 9/2 is 4.5, so it'll be 1.5. We have 2 minus 1/2, which will be 1.5. So we have 1.5 minus 1.5, which will be 0. And for this next one, we have 25 over 2, which is 12.5. Then minus 20, which is negative 7.5. Then here we have 9/2, which is 4.5, minus 12, which is again negative 7.5. So we have this negative sign here. So we have negative 7.5 plus 7.5, which is 0. So A naught is going to be 0. Now that we have A naught and our equation for A sub n, where A is equal to negative j times pi n over 2, we can verify that this equation is correct by using Python. So in Python, I've created a function that uses the equation found in the last step to calculate the coefficient for any given number harmonic, and I loop through the first 100 harmonics, and I use the Fourier series equation to reconstruct the signal. When I plot it, it looks exactly like the signal we started with, so I have verified that the equation found in the last step is indeed correct. So thank you for watching.